Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Button, and I have to not hit this button, and then I think we're live. Is that working?
Hello, everybody.
Every week it's the same.
On.
I'm just hitting buttons and then hoping it works.
Hi, everybody. Welcome to another Ask Us Anything about electrochemistry. As always, please let us know if you can hear us. If you're watching right now, just to give us a good audio check. We always want to double check all the technical issues that could happen, that do happen with live streams. So please let us know if you can hear us, if there's any choppiness, if there's any random stuff like that. But for those of you watching, thank you for joining us. I'm Dr. Alex Peroff. I'm with my colleague, Dr. Neil Spinner. We're both electrochemists at Pine Research Instrumentation, and we do a lot of YouTube videos, live streams, webinars, email, phone. We always get a lot of questions about electrochemistry, and sometimes those other platforms, like just the comment section of YouTube or email, usually isn't sufficient enough to answer your questions, these fundamental questions about electrochemistry or technical questions about experimentation, which is why we do this Ask Us Anything about electrochemistry live stream. So thank you for joining us. We typically, at least for the last several episodes, like 10, 20 plus episodes now, we've been doing this for about 2 hours. So we'll be live for about 2 hours. We're using Restream as the studio platform that broadcasts to YouTube, and maybe we'll expand that to other platforms as well. But in this space, we've noticed there's maybe about a 20-second at max delay between what you observe on the live stream on YouTube and what we see in the chat. So just be mindful of that as we answer questions. If you are watching this after the live stream has aired, there will be in the description below, we'll have all of the questions in the description, so you can skip to where which question you want to get an answer to. As always, there are no dumb electrochemistry questions. This is a safe space where you can ask us anything about electrochemistry, hence the name, Ask Us Anything about Electrochemistry. And we're going to try our best to answer them. And I think the last, boilerplate thing is we
will say your name wrong.
Yeah.
But in our defense, we're reading your YouTube account name.
Yeah.
Which is not necessarily your actual names. I think sometimes it is, but sometimes it's like RFC219713. It's like a Star Wars character.
Yeah. Yeah.
It's like
or Pokemon.
Or Pokemon. Yeah.
Yeah.
We had someone who was a Pokemon once.
Yeah. Yeah.
And I don't know anything about Pokemon, but we have it on good authority that Pokemon is an electrochemistry hot, ground, right?
Yeah.
They're electrocuting and sending fireballs at people and doing electrochemistry. That's what's happening.
I think there's a Pokemon called Electrode.
Oh, is there?
I think so.
Doesn't the yellow one do?
Pikachu.
Yeah, that guy. He sends electric bolts or whatever. He's an electrochemist.
He's an electrochemist.
Yeah.
Just whenever he fights a water Pokemon, electrochemistry is happening.
It's easy.
You
Yeah.
just need a rock water type Pokemon fighting an electric type Pokemon is electrochemistry.
Unless the water is perfectly deionized.
Yeah.
Then his electricity is useless.
Yeah, that's right.
Oh,
That should be an ability. They should add that to the game. Ability,
he adds
deionization.
deionization, or he has the ability to add salt to the water
Yeah,
to make it more conductive so he can electrocute his victims.
ionization.
Ionization or deionization.
Deionization.
Yeah.
Well, thank you all for joining. Also, one thing we've recently added to the live stream is if you are a tier 1 or a tier 2 member, there should be a comment in the YouTube post that will give you a link to join us in Restream, in this platform, where you can actually share your data and talk to us, not just typing your questions, but actually we could see you. Although,
Talking.
or yeah, talking.
This is typing.
This is typing.
This is singing or talking.
This is talking.
You can sing us your question if you have a good voice.
Yeah.
So yes, either way.
Yeah. So as always, please type any questions you have into the chat, and we'll try to answer them as soon as we can. And if you want to join us, try to go to that link, or if you're a member and you can't find that link, let us know. But it should be in the community posts. There's a post with a Restream link, the most recent one, and putting that into your web browser should allow you to join this channel. So yeah, I think that's about it.
Okay. Well, we did have one question that was on. It was this morning actually. So I'm not sure if it's even still there. Sometimes YouTube does this weird thing where it like just eliminates the questions after some time. So I always check on it and make sure to like add them into our little platform here ahead of time. So I'm not sure if this person is here now or perhaps you will see this later. But Sophia Getzi asked, I have a doubt regarding Tafel plot in electrochemistry. Can you please explain how to plot it from a linear sweep voltammetry graph? And then what does the decade refer to in that slope calculation? Okay, so Alex is looking at me because this is one of my trigger
trigger phrases.
This is one of my trigger warning phrases for me. Tafel plots are a sore spot for me.
Yeah.
So the first thing that I will tell you, it's just related to what drives me slightly up a wall, is you have to be very careful if you are going to take a linear sweep voltammetry and try to do Tafel analysis to it. Okay. And the reason for that is because Tafel analysis implies kinetic information only, 100% kinetic information. So if perhaps there's time or if someone is interested, I can show the couple of derivation steps. But basically the Tafel like equation where you get the Tafel slope from is a direct derivation from the Butler-Volmer equation. The Butler-Volmer equation describes the kinetic current as a function of overpotential. Okay, so what this means is that if you do a regular linear sweep voltammogram or voltammetry experiment, just sweeping on your regular 3-electrode system, let's just say, it's almost guaranteed that you are not getting only kinetic information. It's almost going to be impossible for you to do that. There are ways to isolate kinetic current and kinetic information, like rotating electrodes or microelectrodes or some other things, usually where you're, controlling the mass transport, and you can sort of do one of these like kinds of analyses like Levitch or Kentucky-Levitch or kinds of transforms and processes of the data where you sort of extract from the overall current or the mass transfer limiting current, stuff like that. You can extract the pure kinetic information. In the absence of that, making a Tafel transform might be instructive, but not accurate, because you're transforming your current into a Tafel plot, and it's not kinetic information. So your Tafel slope is meaningless, or almost meaningless, I should say, because you're applying an equation improperly. Okay, so with that caveat aside, I will show you some Tafel analysis. Let's see, I'm going to share our software here. Let me get the right window. That is it right here. You make that question go away, I guess, if it's in the way.
No, that's okay.
So, for example, if you have a linear sweep voltammogram, linear sweep experiment. So in this case, this is actually almost cheating, I guess. So I've already sort of swapped. So if you do like an LSV with your average potentiostat, you're going to get current versus potential, not always potential on the y-axis. I've already flipped these axes to just sort of skip a step here. So just bear with me here, right? But this is a linear sweep voltammogram, let's just say, right? I have potential gone from one point to another point, and I'm measuring the current. So a Tafel analysis of potential current data, actually both people do both. This is the one that I prefer, is where potential or voltage is on the y-axis and current is on the x-axis. And so what you do is you basically take the logarithm, the log base 10 of the x data. Okay, so this is actually a Tafel plot. So I'll fix this label's actually, it's actually the log of current, and it's actually technically it's unitless. Okay, so this is actually what, and this data, by the way, is just from something else. This is like an LSV for, like, you can see, like, it's a solar cell. It's from some other thing. So the actual numbers here are irrelevant. Don't worry about the numbers in the curve that you're seeing here. I'm just trying to show you the process, if you will, that you would do to make like a Tafel analysis. Okay, so what you would do is, and again, the units aren't going to be accurate, and that's fine. I'm just showing you, roughly speaking, this process. Okay, so you have your LSV has now been transformed to a Tafel graph, with Tafel X and Y, if you will. Okay, which is potential or voltage and log of the current. It doesn't matter if I started in milliamps or I started in amps or I started in microamps. It doesn't make any difference. The Tafel slope would be the same. And that'll get to your last question, which was about what does that decade mean? And in short, what it means is decade of current. Okay, because you're taking the logarithm. So the word decade, usually we think of as 10 years, but right, decade in this sense is, it's a what, by 10, or what's the right wording here, right? It's the log of 10, right? It's
what a decade.
Like, yeah, like when they say like millivolts per decade, it's decade of current.
Yeah.
So it's like,
so it's a factor. Yeah, it's a
factor of 10 of current.
Yeah,
something
so
like that. Yeah.
Yeah, so like
Whatever
there's
the
like
right.
10 milliamps or 100 milliamps, and then 1,000 milliamps. Which one of those is?
This is one of those
decade.
things that the word, I think, trips people up because they think like, I get 10 millivolts every 10 years. That doesn't
Yeah,
make sense,
that's right.
Because it's just, I don't know, decade.
decade.
The word decade kind of throws people for a loop. At least it did for me when I was in graduate school.
Yeah.
So, but anyway, all that means is that it's log base 10 of current, and so right, if you started with amps, this is whatever. This is like -1, -2, -3. If you started in milliamps, this would be -4, -5, -6, or something. But it doesn't matter, that the slope will be the same because it's because of the logarithm. It makes no difference. So anyway, I think that's relatively it, with the caveat that I gave about being careful that your data is, or at least knowing, right, that your data is, if it's purely kinetic or not. You want to be cautious about diving ahead with Tafel analysis.
Yeah.
Okay.
Yeah.
So there you go. So decade is decades of current. That's what where decade comes from. And then really the only other way, and you've drawn this picture before, sometimes it's the other direction, where current is over on the y-axis, potential's on the x-axis, and you draw the curves, and then your slope would just be the inverse of it, right? If you have the axes reversed, you'll take 1 over your slope, and that's millivolts per decade, and that's Tafel slope.
Yeah.
So
that's true. Hopefully that's helpful.
That's a concise answer there.
Okay, so we have a question from Shubham, which I think is a returning person. You've been with us a few times. It's great to see you. So Shubham is asking, there are usually 2 semicircles in Nyquist plot, which are most often related to solution resistance and the other to charge transfer resistance. But what does it mean when the third semicircle appears? Well, I think there's a bit of a clarification that needs to be made, because typically the solution resistance doesn't have a semicircle associated with it. It's
Yeah.
actually just like, it's just a pure resistor. So if we let's see if I just share screen and then go to just to kind of show you. So generally speaking, when we model an EIS system, we have one electrode on one side, we have a resistor, and then we have a capacitor or a CPE, and then we have another resistor. This is our Randall's element. And the Nyquist plot for something like this, just this, would just be a semicircle. And you have real, Z real is here, Z real. And then you have negative Z. Oh, God. Imaginary.
You could just use an I.
It's an I.
Don't spell it all out. It's too many letters.
Too many letters.
You're running out of space.
But this resistor here corresponds to just the distance between this, and that's the solution resistance. So this is mostly a point of clarification. Like when you like, the solution resistance shouldn't correspond to a semicircle, but every semicircle, to my knowledge, corresponds to a it's called a Voigt element, a capacitor and a resistor in parallel. So no matter how many semicircles you have, those are usually associated with multiple Voigt elements. So if you have a Nyquist plot that's got, like, I'm just making it up, maybe they're spread out, and then maybe it has a diffusional tail or something.
Draw 9 more.
9 more, right? Each one of these is
that's a mountain
corresponds to one of these. So to one of these. So so that's kind of what it means. And I think the question, or the science, and what people typically do is they think about what their system is and try to come up with an explanation as to what this is. And we call this charge transfer resistance for something like just the electron transfer for a molecule at an electrode surface. But when you have multiple processes, there may be multiple things going on where there's different charge transfer resistances and capacitive elements and layers. So Neil, I know maybe if you want to talk a little bit more about some of the other possible things I've heard about, like adsorption and different electron transfer processes being involved, but I don't know. It depends on the system, really.
Yeah, I mean,
what these other things come from.
I don't actually have anything to add.
I actually said all the things.
Everything you said is exactly correct.
I said all the things.
You said all the things. I mean, that's exactly it, really. I mean, just to sort of, I don't know, restate what Alex, basically what you just last said, is that number one, clear up your sort of understanding about what that, if a semicircle you're interpreting as solution resistance, most likely you're misinterpreting that in that way. And that it is related to some process. Now, the only thing I guess I would add is that each of those semicircles is related to some charge transfer process, but that there's a wide range of what that could be, what those could be, right? Whether those are a substrate film interaction. So, for example, one thing that you will see if you're doing like thin film electrochemistry, is like one small semicircle at the very beginning always. And no matter what you do with your electrolyte or potential you're at, that little semicircle is always the same. That's usually an indication that it has to do with your film, because the film is the only thing that's not changing. You change your voltage that you're applying. You go at OCP, and then you do it at 500 millivolts, and you add some gas in the solution, or you take away the gas, but that little circle is always still there. That's usually an indication that, well, the only thing that's constant across all those tests is the substrate in the film with the electrode. So it's more intrinsic to the electrode. That's not solution resistance, though. It's a process, right? It's an interaction of your electrode and your film, or something of that nature, right? And then otherwise, that's a very specific question to your science, right? What's going on? What are the electrochemistry you're studying? What other processes could be occurring. You
Yeah.
know, there could be secondary or tertiary, I don't know, reactions occurring on your electrode at various frequencies. And as the semicircles go from left to right, like Alex was drawing all the different bumps going forever to the right
Yeah.
on a Nyquist plot, that indicates more charge transfer processes with decreasing, I should say this, increasing time constants. In other words, they are slower,
Yeah.
right?
Yeah.
They're getting
That makes
slower
sense.
and typically increased capacitance, which because the time constant is R times C.
Yeah.
And I mean, the resistances could be bigger or smaller. That's all. That depends on a lot of things. But generally speaking, the semicircles appear in order of their capacitance from smallest to biggest.
Yeah.
So the semicircle most on the right corresponds to the slowest process with the biggest capacitor, which is also why it's slow, because it takes a while to charge up a big capacitor.
Yeah. That makes a lot of sense.
Right.
Yeah. Yeah.
Yeah.
Oh, that's good. That's it. Okay. All right. Moving on. We're getting a lot of questions. Thanks, guys. Singh, Vashishta. Hi, sir. I don't know how to answer this question. I looked at this. Hi, sir. I am now just getting interested in nanomaterials, but it's hard for me to find in my college. But I be doing research on Nasicons.
Nasicons?
So how can I can in future see for nano batteries and SEI nanomaterials?
I don't know what Nasicons is. Is that perhaps
I did a very quick
is there a
search.
misspelling or is that actually a thing that I'm not sure
The
of?
only thing I've seen is
Sodium
it's a
ion
sodium
superconductor?
ion conductor,
Interesting.
which I don't know very much
So that
about.
is a thing. I have not. So is this like a sodium ion battery nano batteries? This is not something. Let me see here.
Nasicon compounds have high ionic conductivities on the order of 10 to the minus 3 Siemens per second, which rival those of liquid electrolytes. They are caused by hopping of sodium ions among interstitial sites, Nasicon crystal lattice. So it's like, I guess the conductivity is based on sodium ions moving through them, and it's this incredible crystal lattice.
Sodium, zirconium, silicon, phosphate of some kind.
Yeah.
It's a sodium, zirconium. Interesting. So silicon, phosphorus oxide.
Yeah, and
super
it looks like
ionic conductor.
And it's and it can be a membrane. So a Nasicon membrane is considered for sodium sulfur batteries, where the sodium stays solid. Interesting.
This is lithium analogs.
Oh, okay. So it's
There's
a
a
lithium.
I'm
Yeah, 'cause
literally on
like
the
lithium
Wikipedia
versus
page.
sodium.
Lithium,
Okay.
zirconium, phosphate. So I guess there's because sodium, lithium is smaller than sodium, and presumably, and they're both alkaline metals, so presumably they could both be used interchangeably. This is a field I have no knowledge of, zero. I mean,
Yeah.
I know batteries, but
This is the
if
first
you're
time.
asking if this could be used as some kind of battery or a nano battery or something, my guess is yes. Like it's either for sodium ion or lithium ion. This looks like some really cool, material. I guess it would be a cathode in one of these batteries, maybe, or is it the separator? Because it has, if it's conductive, that's electrically conductive, right? Not ionically, or no, it's ionically conductive.
Yeah, ionically
So
conductive.
these are like separators for batteries, presumably, and I guess they would I mean, I'm totally.
Yeah, we're just learning
At
about
this point now, everything I say could be 100% wrong. So there's my disclaimer for you. But if what I'm seeing here is, if I'm understanding it properly, then everything after this is possibly how this would work, I suppose, just to answer your question as best I can. But I guess this is this would presumably act as like a membrane or like a separator for a battery. I don't know whether the battery would have to be a nano battery or it could just be a macro regular size battery. But if you have some superconducting, because normally the separator is like it's just some polymer, like it's polypropylene, polyethylene. It's usually like some tri-layer with polypropylene and polyethylene, and it's it's just a lattice that's there to soak up electrolyte and facilitate passage of lithium or sodium, whatever ions, back and forth between the anode and the cathode. And diffusion isn't like there's a little fly in here. And it's
same as a little fly. Yeah.
I think this thing has been here for like 2 months, and I don't even know flies are supposed to live that long.
Yeah.
Shouldn't
We'll
it be
have to
dead?
see.
Maybe
Hopefully
it's a new
something didn't like die in this room, and we're just
I hope
unaware
not.
of it.
Yeah, I really hope not, because that's gonna make these live streams way more negatively interesting.
Yeah.
For us anyway. Good thing you can't smell.
Yeah.
Through the camera, but no. Sorry. So
Smell-o-vision.
Smell-o-vision. Smell of YouTube. But so my guess, I suppose, would be that if you have some like super ionically conductive separator in between your anode and cathode, that you would, I don't know, be able to like eliminate diffusion effects, because it would like be so conductive that everything would just go through super easily. Like you would probably have different entirely different transport properties with your battery. What that means is ambiguous to me. Maybe it means you could charge faster. Maybe it doesn't, because there's other problems with why maybe you can charge or discharge at a certain rate, or you still have anode and cathode have their own issues. For example, like the cathode has its own capacity and its own limitations, and so does the anode and stuff like that. So it's like you can improve transport properties. It doesn't mean you're going to get rid of everything.
Yeah.
But that's interesting. And how it would affect the SCI. The SCI usually forms on the anode for the most part. Maybe because the transport's so fast, you wouldn't need an SCI, or maybe you'd need a thicker SCI. Like, I don't know. This is really fascinating.
Yeah.
I might have to learn about this at another time. So that's about the best I can give you, just with a very cursory investigation of this Nasicon thing. It's pretty cool.
Yeah.
If you have a more specific question related to it, or like you can provide a little context or give me I don't know, some kind of reference or something, because I don't have any more information about it, but that's a really cool area if so. But yeah, that's about all I can say about it. I don't actually know anymore, fortunately.
Yeah. So so the next question is from Haman P. Can we use silver chloride electrode in alkaline electrolyte? I think it was fine. We talked about this.
Yeah, we talked about this last week, and actually, there was a bit of a, I don't know, it's a bit of a caveat thing.
Yeah.
So generally speaking, put it this way: typically silver chloride electrodes have a glass body. They don't always. I guess they don't have to. I don't know. Maybe someone sells like a polymer body one, but right. But so generally speaking, you try to avoid using glass with alkaline. Now that's my personal sort of experience and opinion, is that is a problem that's greatly overstated. I don't find it to be as big of a problem as people say it is, for a couple of reasons. Namely that a lot of people are doing like just very innocuous alkaline, like 0.1 molar KOH, or even carbonate solutions that are not they're alkaline, but it's like pH 10, 11, 12, 13, something like that. Not that crazy strong. You're just never you can use all the glass you want. Nothing's going to happen. It's not like people, I understand why. So the counter to that is, if you're doing like 10 molar KOH, you probably should be doing that in like Teflon, or I don't know, like some polymer, because very, very strong alkaline does slowly, but it does etch away glass, silicon. It'll dissolve some silicates like relatively slowly still, but you're trying to avoid contamination with your electrochemistry experiment at all costs if you can, etc. So you try to avoid using glass. But like, I'm sorry, if you have a pH 11.5 solution, you can keep it there until the next meteor wipes out all life on the planet and it will not leak
Oh yeah.
out. It's just not going to happen. So
Mhm.
that people get over concerned about this problem, I find. Um, so generally speaking, the answer is yes, you can, if you have like moderate to dilute alkaline solution and you have a glass, electrode. If you have really strong alkaline, you probably should
Yeah.
consider using something different like mercury oxide, which typically uses KOH as its supporting
Yeah.
fill solution.
Yeah. 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 That's right. All
Yeah.
right. Very good. I actually missed the next. There's another question. There's a question from. If you want to put this up,
Nasicons.
Jithendra
Mm.
Mani Kumar. If you go, yeah, I lost the. Actually lost part of the chat from Restream.
That's unfortunate.
But
I think there was a follow-up as well. Sorry.
there's a follow up from Hemant.
Was not Hema. It was from, who was it? I'm sorry. Who we answered before? I'm forgetting.
Jithendra.
Was it?
Or is it another?
No. Someone said. Wait, did I lose it too? I saw a follow-up from somebody. I could have. So we just answered before this Shabam. So I thought Shabam put a follow-up. Where did it go?
Oh,
Shabam had
yeah,
a
Shabam
follow-up.
put a follow-up. Sorry, and this is also something I
There
I
it
lost,
is.
But
Yeah, that was what.
yeah,
I
if you
was.
want to put
Sorry,
that
I just
one up.
found it. Yeah, Shabam. Yeah. So I meant
Yeah.
to say that those two semicircles belong to grain and grain boundary resistance, but I'm not sure about the third one. So, right. So not solution resistance, but you mean grain boundary resistance. Well, so even then you're still talking about a grain boundary resistance. That sounds like an interface, but like if you have a semicircle, it means there's some interface, right? And so if it's a grain boundary resistance, there must be some coupled capacitance associated with it, is the point. So the third one, grain boundary resistance. So that's usually an in electrode phenomenon. Like a grain boundary is between two parts of your electrode, which clearly has some layers or some, some structure associated with the interface of two parts of something, and that's what's leading to that. So, I mean, maybe the third one has to do with the electrolyte and the electrode interface. Some processes is occurring, some oxidation or reduction process is occurring. I mean, there almost must be, unless your data is poor, and it might be like the illusion of a semicircle, but it's some sort of error of some kind. So do Kramer's Kronig on your data is one of my suggestions. Kramer's Kronig transforms, and that will see if it matches. Kramer's Kronig may not tell you perfectly well that everything is perfect, but if you have very poor fit with Kramer's Kronig, it might be an indication that perhaps what you think you're seeing as a semicircle is not maybe valid or something like that. You might be able to say, well, I can't think of what this would be, but Kramer's Kronig tells me it isn't anything. It's just drift or something like that. So then, okay, so good. I don't have to worry about it. But if Kramer's Kronig tells you that it fits well, then you might have to continue trying to figure out exactly what's going on. But short of seeing your data and knowing the specifics of your system, that's probably the most that we can really suggest, I suppose. Okay, so Jitendra, do you have you back? Do you have stuff, or should I?
Well, Jitendra is asking. Yeah, I can't. I don't have access.
I put it up here. Can you please explain what exact overpotential and polarization driving force types of polarization?
Well, I think there's so overpotential refers to the potential above the thermodynamic redox potential of a molecule that's required to drive the reaction forward. So, and by forward, it's just like one direction or another. So if I just let me share my screen very, very quickly. Let's go here. So if I have let me just do something very simple, like plus an electron, some reduction. It's an equilibrium, goes to B. All right, so we have a single electron transfer process. There is some E naught associated with this process, right? So E naught has some value. Let's call it X. Well, overpotential is just, so when your potential is at X, when it's at E naught, there's basically like a 50-50, like there's just equilibrium between these two species governed by the Nernst equation. But overpotential is just X plus or minus plus some value, some other, let's just call it Y, some other extra potential, also called eta. Like, it's just the extra potential that drives this reaction from one direction to the other. So if you want to do more reduction, you may have to drive this more negatively. And it's beyond that thermodynamic potential for going from A to B. And similarly, you could drive it the other way, and you could get B going back to A, oxidizing and forming A. So that's what overpotential is. It's just whatever this value beyond the thermodynamic potential of the system. And with regard to types of polarizations, I think it's just, you can just polarize it negatively and positively with respect to some reference electrode.
And that's really all every kind of electrochemical test is doing, is you're picking how you polarize it, how fast, when, right? Like if you're doing a chronoamperometry, you're picking your overpotential. So let's say the standard potential, like you said, for your A plus electron goes to B. Let's say that's the reduction of whatever compound, right? And its standard potential is 100 millivolts.
Yeah.
So if you choose on your potentiostat 200 millivolts, your overpotential is 100.
Yeah.
Right. And you're going to drive the oxidation reaction. So the type of polarization, it's an oxidation, or it's a chronoamperometry, or you do a CV where you sweep from 100 up to 200, and you're increasing your overpotential up to 100 at a rate. And so you're polarizing, you're changing the overpotential actively. And then if you go to 0, you're at negative 100 millivolts of overpotential.
Yeah.
Right. Because you're driving the reduction. You go negative of it, you drive the reduction, you go positive, you drive the oxidation. I don't know what other answer there is for types of polarization. That's just it's either direction is what you're driving.
There's no other like potential driving forces. I mean, the only other thing I could say is like temperature, when some people do temperature studies, but that's also that's just mathematically or that's also described in, say, the Nernst equation. There's this like RT, right? And so that T is going to change things, but that's the only like driving force. It's the potential and temperature. That's about it.
Yeah.
So hopefully that answers your question.
Let's see, where are we at here?
Are
you still like?
I won't be. So I only see things from Chris. Georgie has is answering a comment from Anshu. So that was like,
I'll bring him up then. For some reason, your chat's being
It just comes if I just adjust the size of the restream thing, and that's okay.
Okay, I think this is next then.
Yeah, the next question.
Polarization. So, okay, so this is from Aku. Would you have advice on doing EIS without the proper setup? I only have the Autolab potentiostat, I assume. So a 3-neck flask, reference electrode, PT counter, and glass C carbon electrode, which I have modified. I'm not sure why you think that's not proper. What you just described is a 3-electrode setup. Maybe a 3-neck flask isn't the most common electrochemical cell per se, but let me just check for any follow-ups. You talked about
I'm looking for follow-ups, but
useful battery electrodes. I appreciate that.
Who doesn't have any more kind of follow-ups, but that's sounds like a proper EIS setup. It's the cables. Cables make a difference.
EIS without the proper I guess the advice would be similar advice that I would give for almost any electrochemistry experiment, because what you described doesn't sound. I would obviously, I suppose, obviously have to see a photo of it, but without seeing the photo of it, the same sorts of suggestions would apply as to almost any electrochemistry experiment, which is to say that your counter electrode should have a bigger surface area than your working electrode, preferably. You can try to get your reference electrode as close as possible to the working to reduce the ohmic drop, the uncompensated resistance. Obviously everything needs to be in solution properly, but and reduce the cabling if possible. Try not to have like extra lengths of cable or clips from your electrode to your Autolab cell cable. Try to just connect directly to each electrode. Extra cabling will almost certainly interfere with the signal, particularly during an EIS experiment. But otherwise, what you're saying you're using doesn't actually sound improper to me. I mean, maybe it sounds like you're doing somewhat of a homemade cell, but that's pretty common. I mean, people use homemade cells or small little vessels or something, of that nature. And that's perfectly fine. You don't by any means have to use like a, special glass cell as much as maybe we would prefer it because it'd be good for our company. You don't have to use a special electrochemical, glass cell for sure. You can use a beaker, for gosh sake. You can just dump all the electrodes in and run it. Should work just fine. So feel free to follow up, Aku, if you have any. Okay, I can't maintain a nitrogen environment mainly. I need to study the degree of modification of the glassy carbon.
Let's see.
So I guess there's, and just out of concern that the modifying complex might be oxidized. Well, one way to try to prevent that intentionally is to use a reducing potential as your set point for the impedance. Now, it depends what you're trying to study. I understand what you mean is you can't maintain nitrogen environment, so there might be dissolved oxygen in your solution or in the air or what have you, right? And so if there's oxygen, it might be messing with your complex. That's a concern. But remember, if you're using a potentiostat, you're controlling the potential of your working electrode. So maybe it's not a full guarantee, but if you use a negative potential as your set point, let's just say, negative 500 millivolts is your set point and you do impedance at that set point. Again, it depends what you're trying to study, but
ideally oxygen reduction is not happening there.
Right.
So,
well, no. Oxidation of something. You might be reducing, but you're not. Well, yeah, you got to avoid.
Because I'm just thinking he's working in a nitrogen environment.
Yeah, I'm just saying. Yeah, I guess the point is like if you're worried about whatever your electrode itself oxidizing, if you apply a negative potential, it would presumably prevent maybe some oxidation of the electrode itself because it has a negative, relatively speaking, potential being applied on it. Yeah. So maybe that'll help, but I don't 100% know, but hopefully that's, encouraging. I don't see anything that suggests that you shouldn't be able to run EIS with what you're talking about. This was a follow-up here from Jitendra. I mean, types of polarization is activation polarization, concentration polarization, and ohmic polarization. I mean, I think it just sounds like you're talking about polarization is just like deviation from
just applying a potential.
Well, so concentration polarization is like if you have a membrane in two compartments, you have a high concentration on one side and a low concentration on another side. You have a concentration polarization. It's going to drive like ions to flow from one side of the membrane to the other. There's that's a driving force. So I think that an ohmic polarization would be like high resistance to low resistance. Things are going to move from high resistance to low resistance. Like it seems like your question or your point is sort of more about driving force than anything else. So perhaps I could word it this way. When you are doing electrochemistry and you're applying a potential or a voltage, whatever, between 2 points, you're creating a driving force for electrons to go in one direction or the other. When you raise something above a table, you're creating a driving force for gravity to make it drop. that's a driving force. That's a driving force of distance and potential energy to kinetic energy. When you put a membrane in between 10 molar something and 0.1 molar something, you're creating a driving force for ions to flow this direction to equilibrate the concentration. So you're talking about a driving force. Ultimately, is what you're polarizing. You're changing the quantity of two things in comparison to each other, and it causes the flow or the energy to go from one direction to the other. That's kind of what it seems like you're talking about. So like with electrochemistry, like I said, that polarization is a driving force for current flow. That's what electrochemistry is. That's why you apply a potential in the first place, to get electrons to flow in one direction or the other. Otherwise, concentration polarization is like ionic polarization or ionic driving force, right? Ions are flowing from one thing to another. Activation, I don't 100% know.
Sure.
It's like activation energy, maybe. So if you're talking about activation energy, that's like heat driving force, or like if you're trying to get, like some reactions are like fast and exothermic and like highly favored to like, they want to happen naturally, but there's an activation energy. So you have to like provide energy into it. Like boiling water or something, there's an activation energy associated with that. So like water at 100 degrees doesn't necessarily just boil you. There's an activation energy, and then it boils. So something like that. So this is more of a general science question in some sense. You're talking about different driving forces for different things.
Yeah,
that's kind of what it sounds like.
That's what it sounds like.
So I hope that's relatively clear.
Sure.
Because when you're talking about all those different things, that's not all necessarily electrochemical phenomena, which is fine. But that's my interpretation of what you're asking about. I suppose, I hope that's a reasonable thing to answer there. Let's see where are we at? So 3 electrode setup. Okay, we talked about that. Chris is watching the run up for the SpaceX Booster 9 static fire. I don't know what that is, but I commented that sounds more exciting than anything I've ever done or will do. So I guess that's a rocket thing. SpaceX is like the spaceship company. So I guess they're launching a rocket or lighting a fire or both or something. So I hope that's cool. That sounds interesting. Mohammed asked, where can we rewatch? I hope you're talking about SpaceX.
Yeah.
But if you're talking about this,
our
YouTube channel, hopefully you must be on our YouTube channel now. I would presume when this is over, this will just be a video on our YouTube channel, so you can always rewatch. In fact, even right now, if you're watching and you want to rewind from the past, 40 minutes or something, you can just move the scroll bar on YouTube, and it's live and actively rewindable and everything.
Sometimes you have to click on if you're on the Pine Research YouTube page, you have to click live. Like they group videos by category, so there's regular videos, shorts, podcasts, and then there's like live. And so if you want to watch any of our previous live streams, you would look in the live section to find them. Hopefully that'll help you, Mohammed, with rewatching anything that we've
and if you're asking about SpaceX, I don't have an answer for you.
Me neither. Sorry, man. Let's see. Jithendra Mani also has another question about incremental capacity analysis, DQDV plots. And it's like
the peaks we can see.
So I'm just trying to learn about what this technique is. It sounds like it's used for batteries.
Too long.
And it's almost like taking a C. It looks almost like a CV in the sense that voltage is on the x-axis, and
I think I know what this is, but it just feels like a name that I must know it by a different name. Incremental capacity analysis.
And then the do that search one more time. Incremental capacity analysis is a method used to investigate the capacity state of health of batteries by tracking the electrochemical properties of the cell. Well, it's properties of the cell. Let's see if I can get there's best practices for it. but it looks like as the it almost has like a CV like look, like the voltage is on the x-axis,
Yeah, and dq dv.
and then dq
the
dv.
change with charge with voltage. So this is just like looking at
Like the first derivative.
yeah, it's the first. Yeah, this to me looks like you're looking at the rate at which the charging is occurring throughout the charging process.
Oh yeah, yeah.
So like for example, and Jitendra, you can correct me if I'm misunderstanding this. I haven't done this kind of analysis before, though I did do a lot with batteries, but my understanding about what this is something like so if you have a discharge curve or something, you have something like this. And so the first derivative of that, I mean, this is actually more like, this is voltage and this is, you could say capacity, which is Q. So we'll just simplify and call this Q. So the dq dv, it's actually like the derivative. It's like the derivative of the inverse derivative almost, because
oh yeah, if you
X
have
and Y are swapped.
yeah, if you flip the axis.
So I don't 100%.
maybe,
You don't
but-
usually look at it that way. You look at it this way, but it's something
Yeah.
like the rate of change or something. So as best I can understand, that's roughly what's happening. It's like you're looking at dq dv, which would be like the derivative if these two axes are swapped. And I don't know. I don't actually know much about this kind of, I've never done this kind of
Yeah.
analysis. And I don't know that I've looked at papers with this kind of analysis. You see that the second peak is too long. I mean, that would mean that in theory, I guess, that the derivative is high for a longer period of time, which means it's
I also don't know.
changing a lot.
Yeah, I also don't know if
I
this is
don't
like
know.
a steady state type of experiment where it's like, okay, at this potential,
well, if it's
this is the
it can't be
rate.
steady state because it's a charging thing.
Okay.
So like if dq dv means that it's that the charge is changing as the voltage is changing. I mean, all I could guess is just it means that you have like like almost like be careful. I guess I would say be careful you're not overcharging. I'm just sort of guessing here. Again, I don't have a ton of experience, but with this specific analysis, but
Yeah.
if the like rate of change, and again, I'm sort of backwards because like I showed the
Yeah.
axes are, I'm thinking voltage here. So I don't know if it works the same way. I would guess if there's no, I shouldn't talk more about this because I don't think I know enough. I don't think I know
Yeah,
enough.
maybe we'll.
My hunch tells me that if there's no change with charge with voltage, it's actually the ends, the very beginning and the very end. So actually this is the opposite of the derivative, so that the peaks correspond to the flat portion of your charge discharge curve. Because if there is, that means that there's not a lot of change in voltage, but there's a lot of change in charge. So as your voltage, you said the peak is too long. So there's a long second peak. It's almost like you've got a secondary storage process that's taking too long. You might be overcharging your battery. It's my hunch.
Yeah, it looks like.
So that's my guess. I don't know that I can talk more about it. I should probably not, because I'm only sort of thinking it through with you live here based on my understanding of this. But
and when you do just like a Google search and then an image search for it,
yeah,
it's like there's a lot of like peaks and valleys and graphs.
So let me share that. I actually just did a Google search on it too, but I can let me talk through what I'm saying here basically. So
it's like a lot of changes.
Yeah. So like this is a typical charge discharge stuff right here, right? So if you look at this plot, for those who understand batteries pretty well here, where my mouse is floating, right? This is the capacity. So in the beginning of a charge discharge, the voltage shoots up really, really fast. So the voltage is changing a lot, but you're not charging it very much. Charging occurs as you go to the right on this plot, right? So this would be a level of low dq dV because my voltage is changing a lot. That's the dV.
Yeah.
And my Q is not changing a lot. So that's a low dq. So this is like before the first peak. So over here, for example, you see the start, I have no dq dV. Then I have a big peak because it's flat. It's flat. The Q is changing as the x-axis goes out here, but the voltage on the y-axis is relatively steady. And then usually charge discharge tests have something like that, where there's a sort of like one sort of slope, and then it kind of flattens to a different slope. Sometimes it's like, sometimes this is just whatever this material happens to be that I just did a Google search. But sometimes you'll have something like this actually, right? Where it's like two flat levels or something that's like one flat, something like that. So what you might have is that second peak being larger just means that the second charge or discharge process is more, is longer, is contributing more, right? Charging or discharging, or you're overcharging or over discharging because it's like the SEI might be, you might be ripping electrolyte apart, making more SEI. The SEI could be getting thicker. That's one reason why you have like an extended charge discharge profile. So as this is the third time that I'm saying, I am stopping talking about this.
Yeah, because we don't know enough about it, but
it means the intercalation process.
It makes sense.
Yeah. Means the intercalation process in the dq dV. Yeah. So yeah, it definitely has to do with an extended charging or discharging process that's occurring as you're going through your, like towards the end of your process, which may not be a good thing. But that's just my guess.
Yeah.
Okay. Mohammed has a question.
Yeah.
And I guess put SIE. I don't know if you mean SEI. I don't know what SIE is, unless you just meant SEI.
Yeah.
The question about SIE and where and can we use it, and what about the CV? I don't. Yeah. I think it's just a bit of a translational or typing thing here. I don't totally understand where we can use this technique. SIE is again as SIE technique. I don't know if this is something I'm just not understanding.
Yeah, you're describing it as
the SIE exam. That is not what you're talking about.
Probably not.
Yeah, I don't know.
Yeah, Mohammed, if you want to give us some more,
if you can maybe clarify your question. I'm not sure I understand your question, to be perfectly honest. If you're talking about the solid electrolyte interface in a battery, clarify that. And I don't know if what technique you're referring to, or if you're asking a question about the SEI, and if SIE is some other technique, please clarify, because I'm afraid I don't understand your question. So apologies for that. It looks like Anshul had some questions about gold and ITO, and then Chris was
answering them.
So you're talking about
putting gold
onto ITO, and Chris was saying that plasma vapor deposition might be an option. Yep. I think typically putting coating on ITO usually requires chemical vapor deposition, atomic layer deposition, the LDs. There's ALD and CL, right?
Yeah.
Those kinds of things, which typically involve something like an oven or a tube furnace with a carrier gas. It's heated up. You have a sample holder where you put your thing, your ITO or whatever, and you're sending stuff through a tube, or you're just sending stuff at it, sputtering at it, and it slowly builds up a layer. It's like ALD, I think, right?
Yeah.
I think I'm basically describing ALD.
Or in this case, it makes like eight gold atom nanoclusters is what I think this guy is trying to do.
That way. Yeah. So something of that nature, it seems to be what you would be using.
Yeah.
But again,
a lot of trial and error.
This is definitely a trial and error thing. And And the main thing about coding that on is that ITO by itself is not always easy to use as an electrode. It depends on its morphology and stuff, right? So ITO is like a semiconductor, but also it's like usually coated on glass. It's a film on glass, and you can't always use it easily as an electrode. It depends, right? You have to sort of connect to it somehow, and glass is not electrically conductive, right? So you would have to have ITO over the whole surface. Using an ITO electrode is tricky to get the electrical conductivity, to say the least. So what that means is that it's not always easy or possible to do something like an electrochemical deposition. It's possible, but it's harder because you have to sort of work the
electrical contacts.
Yeah, exactly.
Unless sometimes they sell ITO electrodes with like bus bars, these little silver bus bars that go on the side of it.
Yeah,
and
for the kind of conductivity or whatever.
Or just to make electrical contact. Like, oh, I can put an alligator clip on that part of the ITO, the silver bus bar, and then the ITO can go in whatever solution. Sometimes it can be hard to deal with. I remember like Sigma Aldrich, when it was Sigma Aldrich, could sell those. But yeah, well, hopefully, but yeah, you could put that in a sputtering deposition chamber.
Yeah. Okay. Again, I think Mohammed had another comment, but I'm not sure what the context of this is. Oxygen vacancy concentrations just says that you just wrote that. If you have a sort of a clarification, please type it if you can.
Yeah.
I don't know exactly what you're asking. I mean, oxygen vacancies are.
Yeah. It looks like that message on YouTube was actually retracted, so maybe.
Okay. So maybe
okay.
Yeah. Maybe they don't. Maybe they don't disappear on Restream. So, yeah. I if you have some clarifications or anything, please feel free to either join us here on Restream or type your question. Okay. So. Yeah, atomic layer. Yeah, Aku had said atomic layer deposition is expensive, which of course it is. So, but yeah, that's a good way to do it if you have unlimited money. So, Race Bannon.
Yeah,
Race, welcome back.
Yeah.
Usually, Randall's is represented as Z is equal to R plus
CT plus
R with a Warburg element in parallel with a capacitor. I think there's a follow-up there. Randall's circuit is typically, let me see here. Randall's circuit is typically represented as Z equals this right here for batteries. However, sometimes my best fitted model I get is this one. Does that model make sense? Of course it makes sense. Yeah. So I'll draw both of these for you. R plus C and R plus C. Yeah. Okay. So if I'm understanding correctly, Race, please correct me if what I'm saying is wrong, but what I think you're saying is, let's just say circuit simulation. Where is it? New custom circuit. So for example, you could have a resistor and then let me see what you wrote again. R plus R. Yeah. Okay. So you have R with a Warburg element. And then you whoops. And then a capacitor up here, right? So that's I think that's the first one you talked about. So this is one, common circuit model, not just for batteries, heck, for aqueous electrochemistry or whatever. You might have something like this. This is a modification of the Randall's or whatever you want to sort of say.
Say, Neil, I think for some reason, I think Restream's not showing the pop-up circuit because at least I'm not.
You're not seeing it. Yeah, maybe I have to share that special screen. Thanks for letting me know. Hang on, let me see if is that active. Maybe that acts as a separate window. That's a bit bizarre. Yeah, here's the design. Let's see. Is that showing?
So that's showing the circuit.
That's kind of weird. Yeah, it's a whole different. I guess because Restream's not showing my screen; it's showing an application. So thank you for letting me know as I'm talking with nothing. Race, this is the first circuit that I think you were talking about, right? So you have a resistor, and then you have this sort of Randall's resistor capacitor in parallel, and then you have a Warburg in parallel with the resistor to cover diffusional elements. So what you're talking about is that let's just say instead you replace that with a capacitor or whatever. And, you know, the crossover between a capacitor and a Warburg element and a constant phase element are all, it's close, right? You're just talking about a difference of an exponent.
Yeah.
So in actually, really what I tend to do instead is use nothing but CPEs, because I can let these components, basically their non-ideal nature, fall where they may. So I can do this way. So in theory, if I get alpha is 0.5 for this one, then that's a Warburg. If I get alpha is 1, then it's a capacitor.
Yeah.
If these are both, I recognize I'll have to unshare and reshare the right thing. But let me cancel this. I'll probably have to reshare.
Oh, then the
I'm
in
gonna pull up.
aftermath.
Yeah, I think. Yeah, give me 1 sec here.
Yeah,
I gotta.
yeah. And actually, just kind of curious, like, does a because I know there are many different types of Warburg elements, but like the Warburg element in a battery should be like a very specific kind. It's not like an infinite Warburg because
Well, it's
batteries are contained.
yeah, and well, it's tricky, right? So sometimes you still do get what looks like an infinite Warburg because reasons.
Because of reasons.
Um,
Okay.
Sometimes
Yeah.
you get the, and this is this thing too. I mean, I even admit this. I think I try to when I do my like EIS webinar or whatever. I try to admit, like, there's a bit of craziness and hard to grasp exactly what's going on nature to the idea about how do I say the difference between a Warburg short with a Warburg open and a capacitor. Like, they're kind of the same. They have a slight difference in what they physically look like. There's a bit of ambiguity here, is my point.
Yeah.
Exactly what you're seeing. But yes, with a battery, in theory, you wouldn't get an infinite Warburg, but maybe sometimes you do. You see a lot of stuff out there. You see a lot of different things. The point I was making to you, Race, is that this one here, so for example, this is the circuit that you talked about, but I've put CPEs for both. Now, if I set alpha to 1 for both of them, that's just the 2 capacitors. So this is C and CDL or whatever. And, that leads to this, look, Nyquist plot, which means that this diffusional part, or whatever you want to say, is straight up and down, right? If I decrease the alpha to 0.5, it's 45 degrees, and that's my Warburg. That would be if it's a Warburg. So really, it's more like whatever fits your data is fine, but that a lot of times you get something that's in between, and that's why using a CPE is helpful, because you can kind of adjust for whatever that tail, whatever angle it's actually at. That's kind of the point. So your question about they're both valid is the point. It's just a matter of what fits your data best, I suppose, and really using constant phase elements is, in my opinion, a little bit better, simply because it allows you to adjust for whether they're not perfect capacitors. So yeah. So I think you're on the right track for sure, because all those models are perfectly valid, I would say, right? To you can use them all. Either whatever flavor of that Randall's model there.
So there was a question above and from Yogesh Singh Thakur. I think I got that right.
Yeah.
And he's asking, can we calculate theoretical power density and energy density from 3 electrode systems? I don't know. And
I don't know what you mean by theoretical power density. So
yeah, like, are you asking? And perhaps we need a little bit of clarification, Yogesh. But like, are you just like, when I think about power and power density, I just think about multiplying the current times the voltage.
Yeah, that seems to be what you're asking.
And correct me if I'm wrong. That's what you're asking for. And so can you calculate it? Well, you can certainly simulate cyclic voltammograms. based on a variety of different conditions. I will actually, if you want, I can share. Um, this is we have some simulation software, but if you can see, this is aftermath. I'm doing electrochemical simulation for, say, a cyclovoltammogram. But what you can do, and you can put down a variety of different aspects. So for example, the concentration of your species is, I don't know, 3 millimolar or something like that, and you'll notice like, oh, these numbers, like, they change a little bit. The actual concentration, the power, the current here is different. The diffusion coefficient is different. Maybe the heterogeneous rate constant is different. You can change all these parameters. This is all theoretical. This is all based on simulation. And then you can download this. You can take this data and then multiply, whatever current that's measured at whatever potential. Of course, you can also, like, I have it at 0, but you could set this to like 200 or something like that. I'm just going to shift this over, and then you can multiply that and actually get power in watts. So this is all simulated. So there are, I guess, to answer your question very simply, there are theoretical ways to determine power and energy density, and that's from just like a 3 electrode system. So that's what I think you're asking for. But if you have any just clarification, please let me know. Let's see. Going down. So it looks like I think the next question I see is from Salah. And it's what catalysts are commonly used in HER and OER?
Oh, sorry.
Oh, you just
my thing was stuck, and I
okay.
put it back there.
Click it back.
I ruined it.
What catalysts are commonly used in HER and OER? I mean, general idea for beginners, and where should we start from? I would say there are some. What is it? Is it Vulcan Platinum or something?
Vulcan XC72R.
Oh, sorry.
That's the name.
So it's already been discussed here already?
No, that's just what
that's
called.
what it's called.
Yeah, carbon's fine. Even platinum. Yeah. So platinum is, relatively speaking, considered a poor catalyst for HER and OER, but it will do it.
Yeah.
So if you just take a platinum on carbon or a platinum disc, and you just run its potential really, really far negative, you'll do HER. Really, really far positive, you'll do OER.
Yeah.
And you can study those pretty reproducibly, pretty easily. It's a noble metal, so the good news is nothing's really going to happen to it.
Yeah.
Right. Those are not the best catalysts for that. So I think that actually things like a lot of transition metals are used for OER and HER.
Interesting. I always thought that platinum was very good at it, and we're trying to move away from using platinum.
We are trying to move away from platinum, but it's mainly for things like oxygen reduction, not oxygen evolution.
Okay.
So I think that I think things like palladium and some of the other noble metals are better.
Yeah.
And actually, things like I think it's not that they're necessarily bad at it. I just think that there are things that are better.
Yeah.
But platinum is still used pretty ubiquitously, despite how expensive it is.
Yeah.
Because it's so noble, it doesn't, it
doesn't.
It poisons over time with like CO and whatever.
Yeah.
But for the most part, it's a very reliable catalyst and whatever. So, generally speaking, carbon or platinum will accomplish these for you. If you just go to extreme enough potentials, you'll start doing them. And there's plenty of literature out there to study against, of course, right? Because even people who are doing novel materials typically compare it against carbon or platinum, right, as a baseline or something. So you can compare your baseline with their baseline, et cetera.
Yeah.
Right. So that's probably my suggestion.
Yeah. It's good. Just reproduce something simple in the literature.
Yes, exactly.
Okay. Let's see. Satsara, now my restream is kind of caught up now.
Oh, good. Okay.
Can you describe the difference between constant current and constant potential electrolysis? Yeah, I think we can do that. So very simply, and I'll share my screen for this. Let me get rid of this reaction quickly. But basically, when you have a constant, let's say if you have a constant current experiment, so let me type, because typing's
Typing
better.
is always smarter.
Constant current, and then I'll make another one elsewhere. Oops, not comment. I want text box, and I will do constant voltage. Okay, and I'm going to delete this comment here for space. All right, so when you have constant current, you're going to be applying some set current. The potentiostat is designed to just to make sure that whatever current you set is constant, as the name is. So let's just say it's 1 milliamp. And what you'll typically do, this kind of experiment is like a chronopotentiometry experiment. So you're going to measure the, for an electrolysis, right? So you're going to measure the potential E as a function of time. All right. And so potential in this kind of context, the way I think about it is it's like it's the thermodynamic driving force. And so potentiostat in this kind of situation is going to keep adjusting the potential. So it might say here, it might go down, it might go up, it might zigzag, it might do all kinds of things to make sure that 1 milliamp of current is being supplied to the cell. So that's what, and this is good because the current represents the rate. So when you're doing a constant current experiment, it's good from an electrolysis perspective because you'll see in a minute, you want the rate of the reaction to remain very, very fast. Now, when you do constant voltage, you're setting a constant voltage. Let's just say that's something like 1 volt, and you're just holding it. And so you are measuring, this is like a chrono amperometry experiment where you're measuring the current as a function of time. And actually, most of these, depending on it, look exactly the same. They look like this. Just usually it looks like some kind of slow decay. Now, the way I like to think about this is the voltage represents the thermodynamic potential of the system. And when you set a constant voltage, you're making sure that nothing else happens. If your redox system, okay, you start electrolyzing stuff at like 0.8 volts, maybe you apply a slight overpotential so that it's going relatively quickly. Well, it's going to start pretty quickly because it's oxidizing or reducing whatever the species is at the surface, and then it might slow down as there's not as much of the stuff that's getting oxidized or reduced. That might happen as you start to consume material. The rate of the reaction is going to decrease, but you're very safe because you're only applying 1 volt. It's not thermodynamically favorable to oxidize or reduce things like the solvent or chew up the electrode. This becomes a risk when you're doing a constant current electrolysis because your voltage could change in such a way that, to get 1 milliamp, let's say your experiment finished, well, maybe this thing starts to go up like crazy just to get 1 milliamp because now it's going to start chewing up the solvent, right, all of a sudden. Or it breaks apart the electrode. These are all kinds of things. So they both have their advantages and their disadvantages regarding an electrolysis experiment. And sometimes as long as you're watching the constant current experiment and making sure this doesn't happen, this is actually also an indication that your experiment is complete, your electrolysis is complete. It's much harder to do that with this constant voltage experiment. So one of them I think is safer. You're not going to destroy anything, but not as fast. And constant current is, all right, I want this thing to go as fast as possible, but I may risk making and doing all kinds of other things. So that's really the difference between those two.
It's a similar discussion for why galvanostatic impedance can be more dangerous than potentiostatic impedance.
Oh, yeah.
Right. So most systems, except for batteries, namely, people do potentiostatic impedance tests for that reason. Because if you do galvanostatic, you might be sweeping the voltage all over the place and pushing a bunch of reactions or ripping apart or destroying your electrode, and you don't really want to.
Yeah.
So controlling the voltage is safer in most cases.
Yeah.
But yeah.
It
Race
looks like Race
followed
says
up here.
another.
Yeah, sorry. So race. Yeah, you said you use a CPE, but it seems the capacitance fits better. Well, that's fine. I mean, in theory, if you used a CPE and you set alpha equal to 1 exactly, it should fit the same.
Yeah.
So if that is not happening, I hope there isn't a mathematical error in whatever software you're using. And if it's my company's software, please let me know.
Yeah.
I don't believe that's the case. I've not been aware of any, errors of that nature. But if that is happening, I definitely need to know that. In any case, if you are using a capacitor or an alpha equals 1 CPE, where's the diffusion? It's not there. If you're fitting with just a capacitor, you're basically saying there is no diffusion effects at low frequency. And if you're not observing any like 45-degree line and you're observing a straight up and down line, presumably that means that's what the capacitance is showing. Then I mean, I don't know how else to think about it. I guess you're not measuring the diffusion at all. I don't, what is the reason for that? I mean, maybe you're not going, maybe in whatever situation you're studying, you'd have to go to lower frequency, or you don't have any appreciable diffusional impact. Like it's hard to say diffusion is not happening. Like, I mean, in some sense, diffusion is always happening if you have a liquid system. I understand that, but it's like you're just not fundamentally measuring it for whatever reason. That's odd. Or you're misinterpreting a semicircle as a Warburg short, because of a Warburg short, which is a diffusional element through a fixed length boundary, or the straight up and down line could be a Warburg open boundary, because that's also a diffusional sort of, like I was talking about before, some blend of a diffusional slash, what would you say, diffusional capacitive sort of like hybrid almost. There's definitely some ambiguity here. So in some sense, it's like the answer is some combination of you either are not really measuring the diffusion at all, or it's actually misinterpreted as part of like a fixed length Warburg element, something like that, which is, I mean, this is tricky, right? This whole kind of thing here, and again, as always, not to sort of cop out here, but I would need to see the data to sort of, if I could render a judgment on it, what I think is maybe happening.
And Race, you're a member of the YouTube channel, so you can
join us on Livestream and show your data
and share your screen, share your data. And we've had some very productive conversations with people who have questions and just want to show us, like, why is this CV curve or the CIS look strange? Sometimes it creates a lot more questions because we ask questions about it. But you're more than welcome to, and if you want to even aim to do it, well, next time's going to be tough. Neil's going to be traveling for a bit.
Likely be here next time. You can join us in the next 10 minutes if you want.
You can join us in the next 10 minutes.
What I'll show you briefly to kind of illustrate what I mean of the difference. I just pulled this up in our software. Let me try to see if this makes sense. This is a model that has, I know it's hard to see here. It's this picture, but there's a resistor, there's Randall's resistor capacitor. And then instead of a capacitor, I actually put a Warburg open. And so what you have here is a similar phenomenon. This fly is all over my face. So you see this little lagging 45-degree part. That's the diffusional kind of component, but that's affected by this B component. So what you might have is something that's like this. Like maybe this line doesn't go quite as far. Let me make that go not as far out as it. I think I make that bigger in it. No, smaller. There it is. Wrong way. So let's say your data looks something like this. It's like there's this, that might be an aggressively high amount of line, but like there's a tail. Okay, well that looks like capacitance, and this is my Randall's element, my charge transfer process. If B gets bigger, I got to bring this up to a little bit just for comparative purposes. You have a little like 45-degree section before it goes straight up. Okay, but if B is smaller, there's no 45-degree section. Okay, so B is directly related to the diffusion, to the thickness of the diffusion layer. Okay, so what it might mean, for example, one again without seeing your data, but one interpretation of like, oh well, it looks like it's pure capacitance. So where's the diffusion? What it might mean is that you have a fixed length diffusion, but the fixed length is really small. Okay, so that's what I'm showing you right here. This B that I'm moving left and right, changing the Nyquist plot in particular, is changing this like 45-degree section before the straight up and down line. B gets smaller. That means the diffusion layer thickness itself gets smaller. And it's the exact opposite. If B is really, really big, it's basically infinity. This is an infinite Warburg, right? You can see it devolves to an infinite Warburg. So the opposite end of the spectrum is where you have a really, really small diffusion. So you may be measuring the diffusion. It's just that it's a really like really, really tight diffusion layer length, I guess. It's like the opposite end of the spectrum from an infinite Warburg. It's like a really, really, really small finite diffusion, you know, for whatever reason going on. So something like that would be, I don't know, my possible solution to what you're seeing.
So Race just asked,
Hmm.
how should I share the ES data with you? Well,
if you join us on Restream, you can literally talk to us. We'll hear you, and everyone else will hear you. And you could show your camera and show your face. You don't have to if you don't. Certainly, we're not going to force you to become a public figure if you don't wish to.
Yeah. And I just
but you can share your screen with us, and we can share your screen live like this, like Alex and I are sharing our screens. You know, and you can share your screen at, just to be clear, in the software we're using, we can control when it goes live. So like if you join us right on Restream and you start talking to us or something and you share your screen, it doesn't go live until Alex or I click a button. Yeah. So like if you say, oh, here's my screen, and you accidentally shared like your bank account information or something, like we won't put it live. We can toggle what goes like live on YouTube or not. So so you can certainly...
I also just posted in the community section to all tier 1, tier 2 members
the code again.
The code, like just not the code, it's the link to go to Restream. So you should like if you go to our YouTube, go to posts, you should see Race, you should be able to see the link to join us on Restream. So hopefully, if you want to do that, I mean, I think we'll be here, I think, for at least another half hour or so,
give or take. So you got some
on the
time.
question. So you got some time. Of course, I would also say you could also email us too. You know, if that makes us if that makes sense.
Matt Biang, welcome back.
Yeah, Matt Biang, great to see you again. It's been a long time. I lost my. It's like
Did you lose it again?
Yeah, I lost it again because like I double clicked on Restream to like, oh, get to this thing, and then it like resized my.
Note to self: never touch the window.
Note to self: single clicks.
That's bizarre. Well, there's a question here from Mushtak.
Yeah.
It says, can you please explain? Can you send the data via email? Yeah, Race, you can send the data via email. Try first. It might get rejected though. Our email servers are pretty limited.
It can be random
for how large a file. So we have like a cloud thing. So you could send an email to establish, you know, hey, we're communicating through email now. And then like Alex or I could send you a link to a cloud folder where you could, if you have like, if the data is, you know, whatever Excel files or images or whatever it is, it might get like, you might send an email and you won't hear from us, or you'll get a immediate rejection because our company's servers just don't always accept large files.
Strong, we're a very strong firewall. But I put in the in the
our email.
chat, pinewire@pineresearch.com.
Yeah, you can email us there.
You can email us there. Just tell us, we talked. That's actually kind of like a general place for emails to come in. So just mention that you talked to us, Alex and Neil, on the live stream, and we want to talk about looking at EIS data. So you can contact us that way. That's perfectly fine. Okay, Mustaq has question. Can you please explain what should be the order of different tests while testing batteries? Like, which test should we conduct first and which second, and so on? I mean, I think part of me thinks it depends on what you want to do. I'm imagining one of the first tests might be EIS, because it's a very non-destructive technique.
Yeah, EIS is a good test to do anytime.
Yeah.
Right. I mean, it's non-destructive for the most part, unless you're doing it wrong.
Yeah. That's right.
Or mistake. I shouldn't say wrong. If you accidentally put the wrong parameters, it could be quite destructive. But like any test could be destructive if you
if you push
use
the boundaries.
improper parameters. Let's just say. But like if you're just asking for a general roadmap, like what do I do? Right. It's like if you're creating a battery and you're trying to run some tests, it's like like impedance to get a general idea for like that it's working. Even before that, just an OCV test, OCP test.
Oh yeah.
Like if you're making a battery, make sure it has a voltage, make sure it's reading a voltage, right? I mean, I did this when I was in graduate school, like made a battery, thought it was fine, and then it's giving 0 volts or millivolts, and it's like, well, clearly I shorted something by accident. I shouldn't bother testing this. You should have 3 to 4 volts if it's a lithium cell, usually, without doing anything else. That's its standard potential or voltage before anything else is even done. And then you're impedance and simple charging and discharging probably is really the simple answer. And quite frankly, that's often the extent of all the testing that you'll ever do. There's other kinds of more, nuanced or advanced, I guess, sorts of tests, like titration techniques, like PIT and GIT. It stands for potentiostatic intermittent titration technique and galvanostatic intermittent titration techniques, which are variants of charging and discharging. They're just different ways of doing it, where you have charging and rests in one after the other, like your charge rest in a certain pattern. You can get other information like diffusional characteristics and stuff, but otherwise it's really just charging and discharging, which means, the simplest sort of charging what's the word I'm looking for? Like program is like basically a 5-step program. This is like a CCCV test. So you take your battery, if it's fully discharged, assuming, or whatever state it's in, and you apply a constant current, CC, until the voltage reaches some upper limit. And then you do a constant voltage at that upper limit until the current drops below some certain value. That's the CCCV charging portion. And then you do OCP or OCV, rest at your 100% state of charge. And then you have a CC, constant current discharge, usually at the same current that you charged it at, but now you're doing a negative current, so you're discharging until you reach the bottom potential. So that's step 4, constant current up, constant voltage at the top, OCV at the top, constant current down. And then once you reach your lower voltage point, it's a 0%, it's fully discharged. Another OCV step for good measure, just letting it sit there, rest before you do it all over again. And that's what people are doing when they do 100, 1,000, whatever, 500 charge discharge steps. They're just doing that over and over again, up and down, up and down, and up and down. And you're seeing how basically long it takes, because if you know the capacity of your battery, you know how good it's supposed to be doing. You put, a milliamp into it, it should take an hour. So it's a 1 milliamp hour battery. Well, if it takes an hour the first time up and down, and that's great. It takes an hour. And then after 100 cycles, it only takes 50 minutes. Well, it's lost about 16% of its capacity, right? So like that's what people are doing. You're seeing how the capacity degrades over time, the same way that if you're testing oxygen reduction catalyst, you're
Yeah.
seeing how your current changes over time. These are long-term stability tests that you're doing. You can determine some of the numerical changes to the battery doing impedance, like you said too, periodically. You could do it every test, or you could do it every 10 tests. You run impedance and see how the resistances are changing and things like that. And then Chris says you might want to gather thermal data during the testing process. That's also very true. So yeah, I was sticking to obviously just the electrochemical aspects of that. But actually, I did a lot of this actually when I was a postdoc. But short of cutting the battery open and jamming a thermocouple inside it, which is possible but dangerous if you don't know what you're doing. Most people measure the temperature of batteries by just slapping a thermocouple on the surface.
Yeah.
You can check how the temperature changes as you charge and discharge, and it will go up. The temperature will change as you charge the battery. It heats up a little bit, and so you can check, because if the battery were to fail, its temperature would spike, and that could be an indication. That's how they test now, actually. So. So I hope that's a reasonable overview of some of the things you can do. If you have more specific questions about any of those things I just described, Mr. Tuck, you can type, and I'll try to clarify for you. But that's about an overview of battery testing that I can give in 5 or 10 minutes.
It's pretty good. It's pretty good.
Looks like Mapiang has another question here.
Yeah. This might be out of topic, but I have read in some papers where they correlate the degree of crystallinity of the polymer electrolyte with the dielectric and modulus plot from EIS. Is this possible? Well, I don't know enough about dielectric and modulus plot. I mean, it would be, I think that's suggesting that the crystallinity of the polymer changes with EIS. And actually, maybe that makes sense. With the resistivity of a polymer crystal start to change. That's observable in the EIS.
I just don't know what dielectric
and modulus plot.
So the modulus plot, I mean, if you're talking about Z mod,
which I remember we had a conversation.
Yeah, we had a conversation about that. That wasn't what I was thinking it was, right? I was thinking that's not necessarily the magnitude of the impedance.
Yeah,
it's something different, which I was a little bit off on my understanding of what was being referred to with the Z mod. So I don't know if I'll try to remind myself the impedance modulus. It's not exactly the impedance magnitude. Is it like the overall impedance, or it's like the time-based impedance? I don't know if I know, if I remember 100% what like impedance modulus is in comparing with those other things. So that's tricky. Dielectric constant and dielectric loss. Yeah, I mean I know what a dielectric constant is. I guess what I'm saying is getting a dielectric from impedance is not something I'm familiar with. I'm not sure how that's done, or if you can do that. What you're talking about sounds reasonable and sounds like it could be done. And it sounds like the degree of crystallinity within a polymer electrolyte would impact the impedance data fundamentally. As far as how it's correlated or how you do that quantitatively, I don't know. But it would make sense that the rate changes based on the structural changes. Yeah, exactly. Exactly how that happens, I don't know though. And I still have this sort of fundamental misunderstanding of this impedance modulus as exactly what that is, because, and again, part of my misunderstanding is because even like my company or like a lot of other electrochemistry companies, for example, call like the absolute value of Z mag or Z mod. These are interchangeable terms. And so I don't know if when you or anyone for that matter is referring to the impedance modulus if you mean Z mag, or it's a different phenomenon because yeah, most like electrochemistry companies, like on a Bode plot, it's frequency on the x-axis, and then it's phase angle on the right axis, and it's Z on the left axis. Now that again, that's Z magnitude or Z mod. These are all used interchangeably. And so if the modulus or if the modulus is referring to something else, it eludes me exactly what that is, if that's the case, and if so, what it is. My understanding is that that's just another name for the magnitude of the impedance, which is basically the Pythagorean combination of Z real and Z imaginary.
Yeah, it's like I'm just looking up like modulus means like absolute value.
Yeah, I think it's the same thing, right? That's my understanding.
Unless it means
which the absolute value of the impedance is the square root of Z real squared plus Z imaginary squared. Like that's what it is, right? It's just it's the hypotenuse of the Nyquist plot.
Yeah, that's right.
It's a directly measured. It's the ratio of the amplitudes of E and I.
Yeah,
it's effectively Ohm's law. So that's all my understanding of that. And so how that relates to the dielectric constant, I don't know actually. And how that relates to the crystallinity of the polymer, I suspect it does, but I don't know how. It's interesting.
Yeah.
So
I think it's possible.
That came back last time, and again, it was like, I feel like the last time this happened, whatever, a few weeks ago at this point, or maybe a month ago or more, the modulus thing, someone was saying it was something different, and I wasn't. I think
the question is, what is the modulus of the impedance?
Well, modulus
and
is
we're just like
modulus is, like you said, it's absolute value.
Yeah,
like it's the
that's what it means. In
yeah,
mathematics.
like so it's the hypotenuse on the Nyquist plot. I mean, yeah, I don't know.
Yeah,
and I understand dielectric to a certain extent, but not to a high enough extent to draw the connection between like EIS data and extraction of a dielectric constant or dielectric loss or anything like that. That's a level of analysis that I'm not familiar with.
Yeah,
to be honest, that particular the only thing I could say about dielectric for like as it relates to a capacitor, it's like if you have a very poor dielectric, your capacitor will be very bad, a very low capacitance value. And there's a lot of things associated with a low capacitance value, like very high impedance, right?
Yeah.
Whereas a high dielectric constant. So maybe that's part of the answer as I'm talking myself into it. It's like, if the impedance is really high, it might insinuate a low dielectric constant in some way. I mean, it depends on the frequency and it depends on probably other things, but like in some manner of thinking that makes some sense, right? Like high impedance means low capacitance for whatever frequency, and a low capacitance occurs because of a very poor dielectric in some ways, right? So if you have like, let's say, I would assume higher crystallinity gives it a worse dielectric constant, maybe because it probably is a little worse. Maybe that's not true. I don't know. Let's just say, for example, in this case, that high crystallinity means that the dielectric constant's bad, right? And a bad dielectric constant will lead to a higher
relative permittivity,
higher impedance. So maybe there's some correlation there. Yeah, what is relative permittivity?
That's what
Chris says.
Permittivity. Let's see, Wikipedia. Factor by which the electric field between the charges is decreased relative to vacuum. Which is and the dielectric constant is the ratio of the permittivity of a substance and divided by the permittivity of vacuum.
Right. Yeah.
Okay.
Which is why that constant often appears in equations, the permittivity of vacuum or whatever. It's it's a value, it's some number.
Yeah, it's a constant. Okay, so Race just said that he sent us an
sent the
email.
Yeah,
Let's see.
we'll look for it. It might get stuck in
Just a
our
second.
filters. So once it's sort of released, we'll take a look at it. I'll take a look at it for you.
Interesting. Okay, so looking at what Chris said, chemistry, the relative static permittivity of a solvent. It's a relative measure of its chemical polarity. For example, water is very polar. Has a relative static permittivity of 80.10 at 20 degrees, while hexane is non-polar and has a relative static permittivity of 1.89. I guess all right, this is important when preparing separations, polar versus non-polar. The correlation should, however, be treated with caution. For instance, dichloromethane has a value of epsilon R of 9.08 and is rather poorly soluble in water. At the same time, tetrahydrofuran has its permittivity at 7.52, but is completely miscible with water. In the case of tetrahydrofuran, yeah, okay. Comparing values. Yeah, okay. No, that's interesting.
Yeah, I'm not sure we can really comment much more on it. I don't know if I know enough more to comment on it, but oh, the modulus that Mapyong's talking about is this M prime is omega C, basically I think C imaginary, I guess. And then omega double prime is, or M double prime is omega C times Z real. I don't really know. It's almost like an inverse capacitance. It's like instead of 1 over omega C, you have omega C. So it's some interesting modulus that like some value that's like related to the inverse of the capacitance. And that's a bit bizarre too, because is that modulus have units of ohms squared?
Yeah.
Because 1 over omega C gives you units of ohms. So
and where are
or
you
no,
also
I'm
getting
sorry,
this formula?
that's
Is this in Wikipedia?
1 over ohms. No, okay, so that's unitless. Those things are unitless. C is the vacuum capacitance, and that's a unitless quantity.
What is the vacuum capacitance?
Yeah, I don't know. This is outside of my. This is completely outside of my my knowledge base for sure.
Yeah.
So yeah, these are some unitless modulus like unitless quantities, I believe.
Okay.
Because omega C is 1 over ohms. So I had it backwards. 1 over ohms times Z is ohms. So it's a unitless, some kind of unitless modulus. It's interesting. I have no idea what this purpose is. This is not something I've experienced with.
Yeah. Okay.
But yeah, that's kind of interesting. Yeah, sorry I can't really be more helpful with you.
Yeah.
But good luck.
Yeah.
I guess. Yeah.
Vacuum capacitance is with mu
equals 1, if you remember correctly. I don't know. This is beyond me. I'm not smart enough for what we're talking about right now.
Yeah, I just don't know. Like,
I'll
start looking up. I'll start looking up vacuum capacitance and try to I need to conceptually understand what some of these like things are. Like what vacuum capacitor. Looks like maybe or vacuum capacitance. Yeah, I'll look some of these things up probably later.
Yeah. Well, okay. I guess we can sort of put a pin in it here, I guess.
Yeah, I think so. I think we've answered a lot of questions. It's been about 2 hours now.
Yeah.
And looks like there's also no more questions. So with that said, thank you everybody for joining us for another episode of Ask Us Anything About Electrochemistry. A lot of stuff that we don't know about electrochemistry, but we try.
Yeah, we can just start titling this we don't know anything about electrochemistry.
Yeah.
I feel like that will attract fewer visitors.
Yeah,
but,
that's right.
Perhaps it would be accurate. Yeah. So
but thanks for joining us. I think next 2 weeks, I think you probably won't be.
I may be here 2 weeks from now. Next week I might pop in.
Maybe. Yeah.
From the airport.
Yeah.
I will be flying around when this is happening next week.
Yeah.
And the week after, I may be able to join. We'll have to see.
Yeah.
Time wise.
Yeah.
But
we'll have to see time wise.
We'll do what we can, I guess. But
we'll do what we can. One way or another, we'll try to do it, and we'll put posts up and things like that.
Yeah.
And things like
cool.
that.
All right. Well,
Thanks
hope everybody
for
has
joining us.
a great weekend, and
We'll see you later.
take care, everybody.
All right.